Hey guys, what's up? Welcome back to the classroom. It's Mr. Low, and today we're gonna go into chapter 6, energy. Right, so energy is something that you might have already learned about in primary school and even in lower sec. Right, but just to take note that when we come to our new syllabus for upper sec physics, the way that we talk about energy has changed. Okay, we'll talk about it more later. Alright, so first of all, let's look at the objective for this section here. We are to understand that there are different energy stores. I'll talk about this more later. Okay, and then we also need to understand that energy can be transferred from this one store to another via these four processes: mechanical, by heating, by propagation of waves, and last but not least by electrical current. And then we also have to learn about the formula for this kinetic energy and this gravitational potential energy. So two formulas for this section. You need to know the formula and use it to solve problems. Right, so without further ado, let's dive right into it. So first of all, we talk about this thing called stores. In the past, we used to talk about different flavors of energy. So for example, kinetic energy, gravitational potential energy, heat energy, so on and so forth. Right, these are different flavors of energy. But in your new syllabus, we no longer talk about different flavors of energy. Rather, energy itself is considered as one type. There is only this one type of energy, one form of energy, but there are different types of stores. So for instance, there is kinetic store, there's gravitational potential store, should be GP, sorry. Gravitational potential store, internal store, which we know as heat energy, and for example, elastic potential store. So the same type of energy, same form of energy, can be placed in different stores, which results in the different flavors of energy that we used to know. Sorry, it's GPE, not GP, GPE. And then internal store, which results in so-called heat energy, and then your elastic potential store results in EPE. Right, so remember, energy in our new syllabus now is considered as one type, one pure form, but it can be placed in different stores. Okay, in the same way, let me draw another analogy that I mentioned about. We have our Singapore dollars, SGD, Singapore dollars, but we have our different banks like UOB Bank, OCBC Bank, DBS Bank. These are the three local banks, right? So the same Singapore dollars can be stored in different banks. See, so now we no longer have UOB money, we don't have OCBC money, or we don't have DBS money, but we only have one type of money, which is Sing dollars, that you can place in different banks. Likewise, one type of energy placed in different stores. So it's a change in concept here, the way that we view energy here. Of course, this is not the only change. Later we'll see there are more changes. Okay, but first of all, energy is the capacity to do work. Means that I must provide you with energy in order for you to do this thing called work. Okay, now this thing called work, it's not the usual homework or when you go to office you do some work. This work in physics is something very specific, which we will see at the end of this chapter. Right, so we come to that later. But first of all, SI unit for energy is joules, and then it's a scalar. Remember, scalar has no direction, right? We do not require a direction to describe energy. Right, so as of all energy, all types of energy, they are measured in joules. So all the different types of stores, energy stores that we need to know. Okay, nuclear store hardly seen in questions, well, because it's really complicated. The more commonly, the more important ones, okay, this is our GP store, our kinetic store, and our internal store. Why is that so? Because there are parts of chapters, our whole chapters dedicated to this. So only nuclear store is hardly seen because it's pretty advanced physics. Okay, so another thing new about this new new syllabus of physics is that we are now focusing on transfer of energy now. There's more emphasis on the way that we transfer energy from one store to another, or from one object to another. Okay, so there are four different methods that you need to know. Okay, so first of all, mechanical methods. So imagine an object that is stationary, that is not moving, right? It's just sitting there. It has 0 KE. But now, when I exert a force on it, suddenly it starts to move. Now, when it has a speed, velocity, or rather, the KE is now no longer 0 because it started moving, right? So you can see before there is no energy in the kinetic store. Now there is energy in the kinetic store. Why does that happen? Because energy is transferred to the object via a force. This is what we mean by transferring of energy via mechanical method. Mechanical means forces involved. Okay, so when you exert a force on an object over a distance, you actually transfer energy to its kinetic store. So this is the case, right? You can see that the speed has changed. Clearly, the amount of energy in the kinetic store has increased due to the force. Likewise, this applied force can result in gain in energy in the gravitational potential store. So before the object is resting on the floor, it's not at a height above ground, it has no GPE here, right? So so the energy in the gravitational potential store is 0 over here, 0 joules. But over here, because it is at a height, the amount of gravitational potential energy is now, it's not just 0, it's bigger than 0 now. There's some energy in the gravitational potential store. Okay, so this is mechanical method by application of a force. Next, heating. So this is quite common sense, right? You have an object that has little or less energy in the internal store. So now, as energy is being transferred via heating mechanism, you can see that the energy in the internal store goes up. So we no longer call it heat energy or thermal energy, but rather energy in the internal store is used. Okay, next we have waves. So waves is something that you may have been familiar with. For example, your ocean waves. You can use a rope or ribbon to create a wave. Right, there are different types of waves, which we will see in later chapter, in chapter 10. Yeah, so just hold on to it first. Okay, so first of all, for example, you have waves coming from the sun, right, that transfers energy in terms of the internal store to the earth. So this radiation that is in charge of transporting so-called heat energy is what we call infrared. Infrared. Okay, infrared radiation is a type of wave that we cannot see with our eyes. You need some machines to detect it. So it is in charge of transferring so-called heat energy to the earth. Okay, this infrared radiation, you will see it in 2 chapters later. Okay, right. Sound waves is also a type of waves. It can also transport energy. So energy from the speakers, right? From when you listen to music, okay, the speakers do transport energy to your ears, right, via these sound waves. Okay, and something that's particularly interesting to me, peculiar to me as well, is that now electricity is no longer considered a form of store. We do not consider electrical energy, but rather electricity is just a way of transporting energy. Right, so now let's just take a note by the side. Electrical current is now a mode of transfer of energy, but itself does not store. Right, so it's just a way of transportation in a way, but it itself does not store energy. Okay, so 4 different methods of energy transfer: by force, which is what we call mechanical method; by heating, using waves; and electrical current. Next, we move into the kinetic store. Okay, so when an object is moving, we all know that it has so-called kinetic energy, right? So it has, or rather, in other words, it has energy in the kinetic store. So we can change this, right? Instead of saying to possess kinetic energy, it's said to, you can say that it is said to possess energy in its kinetic store, right? So this is the proper way of phrasing when we use the store concept for energy. Okay, so let's look at the formula itself, right? So kinetic energy, Ke, is half times m, which is the mass of the object, and the v, which is the speed. So clearly, in order to possess energy in the kinetic store, the object has to be moving. So that's why speed comes into play. But of course, something interesting about this formula is that the speed is now squared. Okay, so you must remember square, and the opposite of square is actually square root. So if your algebra is no good, it's not very strong, here's a little something to help you. Sometimes we can provide you with the kinetic energy, amount of kinetic energy. We can give you the mass of the object and ask you to find the speed of the object, right? So of course, it is recommended that you play with the algebra itself to try to make v the subject. But if you really can't, okay, not recommended, please, as much as possible, do not try to memorize this formula. Right, so how I get this is simply by making v the subject from the original formula. Okay, so m is measured in kilograms, speed is measured in meter per second for the SI energy. Sorry, that's for the SI unit. Okay, next. So let's look at how the formula plays out. If I have an object of mass 10 kg, this is the mass, and you have the speed, which is the v of 5 meters, calculate the amount of energy in the kinetic store. So Ke is half mv squared. We sub in the numbers. M is 10, v is 5, and then press your calculator. It's that simple. Okay, in the second example, you see that the same mass, but now the speed or the velocity is 0. So without doing any calculations, we all know the answer is 0 because simply said the object is not moving. But it is always good to see it for yourself that it is indeed true by mathematics. So let's plug in the numbers. Half times 10 times 0 square. 0 square is just 0. Anything multiplied by 0 is still 0. 0 joules. So this is how it looks like when you play out in the algebra. Next, we look at the gravitational potential store. Alright, so what happens is, if I have an object that is at a height above ground, so it is, by its position, it is at a height of h above ground, then it possesses some energy in the gravitational potential store. And the formula goes like this: mgh, this m is the mass as usual, g, this is something that we have learned in chapter 2, chapter 3, this is your gravitational field strength. Basically saying how strong gravity is at the location. And of course, height above the ground. So you can see that from this formula, right? The greater the height, the greater the GPE. Which makes sense, right? You have to use a lot of energy to push, rather to bring the object to a certain height. So the higher it is, the more GPE it has. Okay, and of course remember that this value of G is 10 on Earth. It's a very nice number. So let's see how it plays out in the formula. You have an object of mass 10 kg. This is your height. Height is 5 meters. So as usual, let's write down the formula first. GPE equals to mgh. Of course, assuming that this is on Earth, right? So G equals to 10 in this case. So let's just sub in the numbers. M is 10, G is 10 because it's on Earth, and H is 5, and that gives us 500 joules of energy in this gravitational potential store. Next, this object is on the ground. Same thing, mass is 10, but it is on the ground now, so we know that H is 0. Without doing any calculations, you should know that the answer is just 0. But let's just see how it plays out. GPE equals to mgh. The mass is 10. G is 10 because of Earth. Height is 0. Anything multiplied by 0 is 0 joules. Okay, so this is how the formula plays out. Okay, in the next section, we're looking at the conservation of energy. This is something that you might have already learned in lower sec, but here it looks a little bit different. Okay, so we have to recall the principle itself of conservation of energy and then apply it to solve problems, right? So the principle goes like this, right? Energy cannot be created nor destroyed, but can be transferred from one store to another. In the past, we used to say transferred from one form to another. But now, we no longer see energy as having different forms or different flavors, but now we consider different stores. So instead of convert, we use the word transfer. Transferred from one store to another, not from one form to another. So this is the first difference, part 1. Part 2, there is an additional line here. The total energy in an isolated system remains constant. Alright, so this is the full principle of conservation of energy. There are 2 sentences here that you have to write in order to achieve 1 mark. It's no longer just the first sentence. Now you have 2 sentences to write to earn that 1 mark in exam. Okay, so first of all, look at the second line here, right? Total energy in isolated system. What does it mean? What does this isolated system mean? You have to take note, you have to understand, right? Okay, that means if I have an object that's sitting there, then does not interact with the surrounding in form of exchanging of energy, then it is considered isolated. Remember, isolation means to be alone, right? To be alone and not interacting with something else. So what is considered an isolated system? So for instance, you have a table and then you have a box just sitting right on top of it. If nothing is disturbing it, it possesses some form of GPE, of course, right? But its total energy, which is in this case only GPE, remains constant because it does not interact with any other objects. So you can consider this box as a system itself. But here comes me applying a force on the object. Now there is energy exchange with something outside the system. And that something outside is me, my hand. And now perhaps it starts moving and then it has some energy in the kinetic store. It has gained some energy in the kinetic store, right? So that is what we call exchanging energy with the surrounding. So for instance, just now when we talk about this Earth and the Sun, if we consider Earth alone as a system, is it isolated? The answer is no, because of this, because we are constantly receiving energy from the Sun. So in that sense, if we consider Earth as a system alone, it is not isolated because it is constantly receiving energy from the Sun. But if we consider the Earth and Sun as a whole system, then yes, maybe it can be considered as isolated, but actually it's not. But in this picture, it is. So energy can exchange within a system itself, but if it's not receiving energy from the outside or releasing energy to the outside, then yes, this system as a whole is considered to be isolated. Right? So if you don't quite understand this part, it is alright. Just have to remember, you just memorize it, okay? So there are 2 lines here for you to memorize. Right? So total energy in a system remains constant for a system. So here, if I input 200 joules of so-called electrical energy, then the output should be 150 plus 50 to give you 200 in total. So no loss in energy, no energy goes missing, right? Energy cannot be converted nor cannot be created or destroyed, so no energy goes missing. Alright, so in this case here we talk about an object falling from a height above ground, and we look at how the energy changes as it approaches the ground. So this is a very typical question. So we can look at the start, right? It is at rest, so no KE, but it has some GP because it is at a height above ground. So in this case, we can consider the total energy of this system. So total energy is the sum of this GPE and the KE, which is 500 joules. Now, as you progress in this question, you will notice that this total energy remains the same, but there can be an exchange between the GPE and the KE. Okay, so let's see how it goes. Now the object falls to half the original height, half height. So that also means that the GPE has been halved. So let's calculate here. GPE is half times the original 500. That gives me 250 joules. Now, because it falls a certain height already, it now has a certain speed, which means the KE is no longer 0. But how much is it now? We are not given information about the speed, so we cannot use half mv squared to calculate. Rather, we should use energy conservation to know that the total energy in the system remains the same. So for me, I can just copy this portion over here and paste it over here to show that, okay, the total energy in this system is still 500. So how much kinetic energy it has, or rather how much energy it has in the kinetic store? It is actually 500, the total energy minus the amount of GPE, and that gives you 250. Happens to be the same amount, okay, happens to be the same amount. Okay, last but not least, we look at the last case just before it hits the ground. Well, just before it hits the ground, because it's so near the ground, GP is 0 joules, right? Okay, now how much KE it has now? We can't solve by half mv squared. Again, we don't have the speed, but again, same as just now, we do know that total energy is conserved. So I can duplicate, copy and paste over here to show that, okay, the total energy must still remain 500 joules. Okay, I can just erase this portion, 500, right? So GP 0, KE must be 500. So you can see that from the whole journey downwards, there is an exchange between GP and KE. 500 and 0, 250 has been transferred from GP to KE as it falls to half the height. And last but not least, at the end, just before it hits the ground, more energy is being transferred from GP to KE. Alright, and now the KE has 500 joules in total, which you observe that, please take note of this 500 joules, should be using highlighter here. Okay, this 500 joules is the same as the 500 joules at the top. So if you compare this, you can simply say that the GP at the bottom here is the same as the KE at the top here. Now, of course, bear in mind that this assumes that there is no air resistance. There's no friction, no air resistance. So if there is, then there will be energy that is transferred out of the ball. The final number 500 for the KE over here will no longer be 500, but something less than that, depending on how much air resistance or friction it encounters. Okay, so for a pendulum, this one you see that this was chapter 1. You can see that at the extreme ends, it is at a highest position, and at the equilibrium position, this is the lowest position. So at the highest position here, you have maximum GPE, but you have no KE, because at the top end, the object is, this pendulum is momentarily at rest before it changes direction. That means for a short period of time, it will be at rest, stop moving before it changes direction. So at the lowest height here, of course, here you have minimum GPE, sorry, GPE, because it has the lowest height, right? But over here, it has the maximum KE here. So of course, by deduction, you would know that the pendulum is actually moving at the fastest speed at the minimum at y, at the minimum position, lowest position here. Okay, so let's see how this energy conservation can appear in question, how it plays out in a question. So let's read the question together. An object has mass of 5 kg. As usual, I like to highlight and take notes. Is dropped from a height of 2 meters above ground. So this is the H. Assuming no air resistance, calculate the KE of the object just before it hits the ground. And then you have your value of G over here. Okay, so this is the case of this, right? The object was at a height, it was released, it was being pulled down by gravity, and we find the amount of K just before it hits the ground, just like this case over here. So bear in mind, the concept here is total energy in that system must remain constant throughout the fall. So what happens here? We first calculate the GP at the top. Okay, so this is the concept here. By conservation of energy, GP at the top here is the K near the ground, which we saw it just now. You can see that GP at the top 500, at the ground K is 500, because all the energy has been transferred, right, from the gravitational potential store to the kinetic store. So we first calculate the GP mgh, and then you get 100, right? So in this case, at the top it had GP of 100, so therefore at the bottom all the energy from the gravitational potential store has been transferred to the kinetic store. So you see that this is a full 100, assuming no air resistance. So here we try a question here. We have an object of mass 4 kg is dropped from a height of 4 meters above ground, again assuming no air resistance. Now we are told to find the V. So this is one extra step here, because in the previous question we found the KE only. Now we have to go and find the speed of the object just before it hits the ground, and we have the G here. Alright, so we should follow the same step as above. By conservation of energy, I'm lazy to write the full thing up. By conservation of energy, GPE at top equals to KE at bottom, just before it hits the ground. Okay, so I shouldn't say at bottom because it's very vague. So you should say near the ground, just before it hits the ground, right? Okay, so we calculate the GPE. mgh, is M 4, or in this case G is 10 and H happens to be 4 as well. This gives you 160 joules. Okay, so we continue the story. As of this, you see that all the energy in the gravitational potential store has been transferred to the kinetic store. So we see that KE near the ground is the same 160 joules. Okay, so from here we can go ahead and calculate the velocity. We want to calculate the speed, you see. Alright, so how do we do that? We recall that K is half mv squared. So I just simply substitute in the number. 160 equals to half mv squared, and we are tasked to find the v over here. The m is 4, so let me substitute in the number. Half times 4 times v squared. So in case your algebra is not strong, let me do the working by the side how I do this. So 160 equals to half times 4 times v squared. Well, we do with the half times 4 first, which is 2v squared. So this is your basic algebra question. 2v squared equals to 160. How do I find v? V squared is 160 over 2. That is 80. So your v equals to square root of 80, which rounds off to approximately 8.94 meter per second. So this is how a standard object dropping from a height scenario can involve the conservation of energy. So we move on to the next section here to talk about this work. Okay, so work done is a very specific term in physics and it has a formula involved. Okay, so we have to recall the definition of work done and then recall the formula. Work done is force times distance to solve problems. So first of all, work is a very specific thing. It means that it is first of all done by a constant force on an object. So that means there must be a force applied in order for work to be done on an object, and that it is the product, means multiply, right? Multiply. So you multiply what? The force and the distance moved by the object in the direction of the force. Okay, so I think a picture in this case is easier for us to see. Okay, so if I have an object that was originally here, there is a force acting on it. Now it traveled a distance. Let's say this distance is d. Okay, I'm using this double slash for parallel. Let me explain what this means later. Okay, so parallel distance. So assuming that the force remains the same and is applied on the object, on this object throughout the distance of d. Sorry, I should use the front marker, okay, for the distance. So now the work done is the force multiplied by the parallel distance. Okay. Now, if you read textbooks or other reference books, you will see that nobody bothered to write this parallel. Okay, this is because two things. Okay, parallel because the distance must be in the same direction of the force. So that means if I apply the force to the right hand side, but the object somehow or another moves in a different direction, then there is no work done by this force. Okay, so it must be in the same direction. So this parallel tells us in the same direction. But for exam purposes, you need not write the parallel sign. It can just be a force times distance. Okay. Now one thing to take note is that work done has units of joules. And you recall that it is the same unit as energy. Let's write down by the side. Same unit as any type of energy. So it's quite interesting here. This work done actually has the same it has the same unit as energy, means that it is closely related to the energy. So we will see how this plays out later. How come work done is so closely related to energy? Okay, so this chapter, the parallel sign also serve another purpose to not confuse with another formula in chapter 5 which we didn't learn. It's out of our syllabus. So don't worry about that. Okay, so yeah, here's the case, right? Okay, if I have a force acting, this guy is pushing towards the right hand side, and then if the object does not move, what does this mean? This means that the parallel distance is 0. Again, by the formula, there is a force but no distance traveled in the direction of the force, then there is no work done. In the second case, is a bit more peculiar. The force is acting upwards, but the object is moving to another direction, to the right hand side. So in this case, there is a force applied, but there is no distance traveled in the direction of the force. Okay, so the direction is different, therefore there is no work done as well in this case. So what constitutes work done, right? So in what cases is there work done? So let's look at two cases. One, you can see that the force is applied to the right hand side and the distance traveled also towards the right hand side. So there is a distance traveled in the direction of the force. In this case, we just multiply the numbers together to get 80 joules. In this case, you can see that the force is applied in the same direction as the slope. So you can see that the object is going to move in the same direction of distance 5 meters as it approaches the top of the ramp or the slope. So the work done in this case, we take the 5 meters instead of the 3 meters or 4 meters, because you can see that the object would have moved here for a total of 5 meters. Okay, so let's look at another question. A container has mass of 10 kg and you take G to be 10. This is on Earth. What is the minimum force required to leave the container? It is good at this time, maybe we draw a picture for us to see, right? So this object has mass of 10 kg and you want to lift this object up. Why do we even need a force to lift it up? By common sense, you should know that because this object has a weight, there is a gravitational force pulling it down, right? So we recall that gravitational force W equals to mg. Okay, so this, since that this is on Earth, this is 10 multiplied by 10 to give you 100 newtons. Now, so this object here has a force of 100 newtons, which means that minimally I need another 100 newtons to start pulling it up. Okay, so this is the answer for part A. So part A, W equals to mg equals to 10 times 10, and that gives me 100 newtons. So this is the minimum force required to put it up. Okay, using the minimum force calculated, calculate the work done. The work done by the force in lifting the object to a height of 2 meters. So now this object is being lifted up by this this force here to a height of 2 meters. Calculate the work done by this 100 Newton force. So let's look at the formula. Work done equals to force times parallel distance. So in this case, the force is pointing upwards and the distance traveled is also upwards. Great, we have work done here. So we take the force 100 multiplied by a parallel distance of 2 meters. That gives us 200 joules. Remember, work done carries the same unit as energy, 200 joules. Okay, next part C. What is the gain in the GPE for the container? Well, we look at the formula again, right? So GPE equals to mgh. Let's look at the scenario here. The h here is 2 meters. So I input the numbers, mass is 10, g is 10, and h is 2. And that gives me 200 joules. Now, here comes the interesting part. Why did I say that work done carries the same unit as energy? We need to compare our answer for part C. Compare that to part B over here. Please change the question here to part B. So essentially, we are comparing these two numbers here, this 200 and the 200. You notice that they are the same number. Why is that so? Okay, the concept here behind is that work done, remember, when we talk about energy transfer earlier, way earlier in the chapter, let me zoom back a little bit. There is this thing called mechanical method. That means it is a method to transfer energy to the object via applying a force. And remember this picture here? When I apply a force to move the object above ground, it gains certain amount of energy in the potential store, gravitational potential store. We see how it plays out right now in this case. Here, the work done by the force is 200 joules, and coincidentally, or rather not coincidentally, the amount of GPE gains is 200 joules. So what does this tell us? This tells us that the force has transferred 200 joules of energy to the object, which is stored in the GP store, gravitational potential store. Okay, so work done equals to gain in GPE in this case, right? Assuming no energy lost to the surrounding by friction or air resistance. Okay, so the work done must be equal to the gain in energy in whatever store. In this case, GPE, right? So this is what we call the work energy theorem. Whatever I said just now, You don't need to know about this, but good to understand that work done the work done on the object or on a system becomes the energy in a particular store. So this is why work done and energy, they carry the same units. This is how they're related to each other. Okay, we come to the very last section of this chapter, power. Okay, so power by definition is the rate of work done or rate of energy converted. This rate here talks about how fast, so called how fast. It has the element of time. Okay, so power essentially is how fast work is done or how fast energy is being converted, or you can say transferred from one store to another. Okay, now the formula P is E over T, or P equals to work done over time, depending on the context of the question. So we look at the question immediately to see when do we use each case. Okay, so P, power, is measured in watts. This is someone's surname, Watt. Okay, so let's look at this case. An electrical heater converts 100 joules of electrical energy to 100 joules of heat energy within 2 seconds. What is the power of the heater? So we look at the amount of energy converted here is 100 joules from electrical to heat, and the time taken is 2.0 seconds. So this is T, right? This 100 joules is the E, and of course here we're using E over T because we're talking about energy transfer over here from electrical to internal store, the heat energy. Right, so 100 divided by 2, that gives you 50 watts. So this is the case whereby you use E over T because we're talking about transferring of energy. In the next scenario, we look at energy output. Okay, so also energy, it can also be seen as work done, but okay, we talk about that later. Okay, so let's read the question first. So Alice ran out of flight of stairs of 12 steps within a time of 10 seconds. So this is the T. The height is still unknown as of now because we only know there's 12 steps. But here comes the next one. The height of each step is 0.1 meters. But we should not write H over here because this is not the full height. Remember there are 12 steps here. So maybe we do a calculation here. Height is 12 times 0.1. And that gives me 1.2 meters. So this is the height. And Alice has a mass of 45 kg. What is the power output during the run? So how fast is she generating energy? So we look at energy as the gain in the energy in gravitational potential store because she's climbing, right? She's ascending, she's getting higher and higher. mgh. So this, bear in mind that this h is 12 steps. So 0.1 times 12, that gives me 540 joules. That means within the timing of 10 seconds, she outputs an energy of 540 joules. Of course, this energy comes from the food that she consumes, so this is considered as energy transfer from chemical potential store to GPE. Right, so we can write down by the side. This is from chemical potential store to gravitational potential store. Okay, from the food she eats lah. Okay, so in this case we're using, again, is energy conversion, E over T. So 540 divided by 10, that gives you 54 watts. Okay, next. Okay, we have a kettle which has a power rating of 1850 watts. So in case you don't know what is the meaning of rating, it's okay. Look at it. Look at the units here, right? W, watt. It tells you this is power. Determine the amount of energy in the internal store. This is the E. It can generate in 1 hour. So this is the trick here. 1 hour we must convert to seconds, right? So 1 hour, how many seconds are there in 1 hour? Answer is 3600 seconds. Why? You can figure it out. Okay, so here we are using the formula power equals to energy over time. Here we are finding the E. The E is the one that we are interested in finding, but let's put in the numbers first. 1850 equals to E over, instead of 1 hour, it should be 3600 seconds. Okay, when you multiply them, you should get approximately this amount. Okay, so this is the amount of energy in the internal store that it can output by the kettle. And we come to the last question. So you have two persons running up the stairs. Alice has a mass of 40 kg, so this is the mass, while Bob has mass of 50. Bear in mind that two different persons here, two different masses, both run up the same flight of stairs and reach the top that is 5 meters above ground. So here immediately they tell you the answer for the value of H. So H equals to 5 over here. Okay, different masses, but same height. And Alice took a time of 8 seconds, while Bob took slightly longer, which is 9 seconds. Who has the greater power output? Okay, so remember, power is energy over time. That means if I can generate the same amount of energy, or rather I can transfer the same amount of energy within a shorter time, I have a higher power output. Okay, so let's look at this. In both cases, they are climbing a flight of stairs. So the energy that we are talking about here is also GPE. Same case as just now, right? The food they consume is being converted into GPE. Okay, so we calculate the GPE for Alice. Okay, we can separately calculate them. So first case here, Alice, and then we do so for Bob. Okay, so the GPE here that she gained after she climbed up that flight of stairs is mgh. For her, the mass is 40 kg times 10 because of Earth times the height of 5 meters. That gives you 2000 joules. Alright, now we do the GPE for Bob first before we continue to find the power. GPE mgh. Bob has mass of 50 multiplied by 10 multiplied by the same height of 5, and that gives you 2500 joules. So because Bob is heavier, you see, so to ascend the same amount of height, to climb the same amount of height, Bob requires more energy, and of course he has gained more energy in the gravitational potential store. Okay, now it's time to calculate the power. Who has the greater power output? It's now determined by the different timing they take. So here, we write down the formula first. Okay, E over T. In this case, the E is the GPE, 2000 divided by 8 seconds. Let me pull out my calculator real quick. You can help me as well to check. So 2000 divided by 8, that gives me 250. Now this is measured in watts because we are talking about power over here. Okay, so let's do the same thing for Bob. So power equals to energy converted over time. In this case, his gain in GPE, or rather amount of energy transferred is 2500 joules. Now he took 9 seconds instead. Bob took 9 seconds here. So I'm going to take 2500 divided by 9. That gives me approximately 278 watts when it's in 3 significant figures. Okay, we compare the two numbers. Clearly, Bob has the greater output. Hence, answer is Bob. So even though Bob is heavier, even though he took more time than Alice, but because he is significantly heavier than Alice, so at the end his power output actually is more than Alice. Okay, so this is it for this chapter. Let's do a quick sum up. So this chapter is about energy. We talk about energy in the different stores instead of different types of energy. So chemical potential store, so on and so forth, right? So just now we were saying that it is the same type of energy, same form of energy, but placed in different stores. Okay, we also talk about how energy is being transferred, four methods: by a force, mechanical methods, by heating, by waves, and by electrical current. Next, we talk about how how to calculate KE, half mv squared. We use it to apply to questions. We also calculated GPE by mgh. We apply it to some questions. And then we talk about conservation of energy, bearing in mind that we now talk about energy being transferred from one store to another instead of converted from one form to another, and that you have a second line here: total energy in an isolated system remains constant. We see how it played out in the question when we talk about a simple case of an object being dropped from a height. We can then calculate the amount of kinetic energy at the bottom. With that, we can also go and calculate the speed of the object just before it hits the ground. Next, we talk about work done. Work done by a force. There must be a force applied, and then there must be a distance traveled in the same direction as the force. We multiply the force and the distance together, you get the work done, which happens to carry the same amount of, the same unit as energy. And why is that so? Because in this example, we see that when you lift an object from ground to a height, the amount of work done by that force to lift it up happens to be the same amount of energy gained in its gravitational potential store. So we can see that work done actually is the same as the gain in GP, therefore they carry the same unit. Last but not least, we look at power. Basically, power is about how fast work is done, or how fast energy is being transferred from one store to another. Okay, we examine a few cases. Here we talk about electrical energy to heat energy. Here we talk about from chemical store to gravitational potential store. Here we talk about electrical to heat as well. And then last but not least, we compared two persons with different masses climbing the same height but taking different times. How do we compare their power output? So with that, we are done with this chapter. We hope you understood what's going on so far. I will see you in the next chapter. Take care.